Welcome to a discussion with Yuta Noma regarding his paper Surface Filling Curve Flows via Implicit Medial Axes. We're going to talk about how to fill up a particular surface with a curve and the specific contribution that Yuta and the team has made toward this research field is to make the process more efficient. I hope you enjoy it. I think a good starting point for us then would be to just describe surface filling curves to begin with. Maybe from an application standpoint would be good because I think a lot of the viewers maybe are not familiar with exactly what these curves do. So if you would mind introducing that just from an application point of view.
Okay, so can I start now?
Yeah, sure.
Okay, so basically this paper tells you how to compute surface filling curves in a efficient and robust way. So basically a surface filling curve is a curve that fills out a surface with a constant thickness as much as possible. And I feel one obvious application is 3D printing, because if you've ever seen a 3D printer that's working, then you see a head of the 3D printer that traverses along a path that kind of fills out the 2D plane as much as possible. And so that is one obvious application. But in the paper, we kind of describe it as a method that has more wider applications. So for example, if you think of a robot that paints a surface of a car that you can see in the paper in the second page, I guess. And then you would also want that robot head to traverse along the path that fills out the surface as much as possible. So yeah, so in the paper, we're kind of describing it as so of course there are existing applications for this surface filling curve, but also there are more further applications that we can apply for. Yeah.
As far as applications right now, do people actually use it for 3D printing at the moment?
Yeah. So for 3D printing, well, I kind of went through a bunch of whole papers before I wrote this paper. But basically, I think people first slice it into 2D planes, and then they draw a curve on top of it such that it kind of gives you a curve that fills out that 2D plane. And so maybe it's kind of related, but maybe it's not. So basically, I think the state of the art does it by creating a curve that fills out the plane, I feel. So maybe it's not directly related, but still, if you think of an example where you only want to fill out the surface, then this method can definitely be applied. Yeah.
Because I haven't looked into any of the applications myself,
Yeah.
whether or not it's actually used for it. I'm not trying to put you on the spot or anything. I'm just thinking when you mention 3D printing, it feels like you want to make sure that each layer of plastic that you put on top of the other is aligned to a large extent as well, because otherwise you might have in some applications, I think they're quite unstable when you do multiple layers, especially if it's a thin construction, that you want to make sure that they're kind of layered so that the plastic is really on top of plastic. But I don't know that much about the 3D printing space.
So I think my point is that the application of our method is not limited to 3D printing. You could go beyond maybe the robotic path planning application that I explained, or maybe machine knitting, or so I think if you see lots of products in the wild, then you'll definitely see lots of patterns that have these kind of space filling nature. For example, if you see your clothing, then you can see that the pattern of the strings are kind of filling out the surface of your clothing as much as possible. So I think that's one potential application. Of course, it's not, used in the actual application scenario, but we feel this is kind of a potential application as well. Yeah.
Okay, let's scroll down to, I think figure 2 could be a good introductory figure. I would like to talk about the existing approaches that handle this, and maybe this one is good just to get a sense for people, what actually happens when we apply these surface filling codes. But would you mind, with this one as context, explaining what usually happens when you try to do surface filling curves?
So do you mean explaining about the previous approaches?
Breaking down the approaches in a bit more detail, what different variants there are in the space right now? and then how you were eventually building on top of that with the solution that you've provided in the paper.
Okay, so basically our method is a geometric flow. So like given a surface and initial curve, then it grows such that the curve fills out the surface as much as possible. So if you see this image, like you start from this triangle that's placed onto this horse, and then it grows such that it becomes a surface filling curve. And in this family of work, one significant work is like named repulsive curves, which was published by you et al. In like 2021. And so what that basically does is first you define an energy function. And then given that energy function, you can take the gradient of it. And then like based on that gradient, you can grow the curve towards that gradient direction and such that it minimizes the energy as much as possible. So
and it's a repulsive energy then that you're introducing as well?
Yeah, so
like,
exactly.
okay.
So it's a repulsive energy. So like basically you define an energy such that like if the two curves become very apart from each other, then the energy gets kind of minimized. So that's one approach. But we also found out that energy is actually not really good in terms of computing these kind of surface filling curves, because first of all, it's extremely slow because it was using this type of matrix called dense matrices, which is a matrix that has lots of entries inside the matrix that such that like, so if you see like an n times n matrix, like almost all of the entries are filled out with an element, whereas like you rarely see elements that are not non-zero. You rarely see elements that are zero. And in that case, computing those dense matrices is of course really computationally expensive. But what's even more expensive is to invert that matrix and do a linear solve. And so that was pretty problematic in their approach. But in our approach, we found out a formulation to instead of using those dense matrices, to use sparse matrices, which is basically you have an n times n matrix, and then the entries are basically zero everywhere except for a really few number of entries. So in that case, of course, the data storage is really efficient, and also doing a linear solve on that matrix is really fast.
Okay. Yeah. So both of these approaches, the one that you're taking and the repulsive curves, I think it was called, the other paper, they're both examples of geometric flow, right? Geometric flow algorithms for doing this. With the context of the figure that we have on the screen, could you explain a little bit what the initialization-based ones are as well? Like how would because my understanding of initialization-based ones is that you sort of postulate a curve shape or something like that, and you apply it, and then you do some adjustments to that. But how would that how would that work in a context like this?
Oh yeah, so I feel like there are lots of literature, especially in 3D printing or kind of stuff. So like basically, first in those initialization-based approaches, they first compute like a discrete set of curves, and then given those set of curves, they kind of figure out a way to connect all of them in a unicursally connected path, and then finally, given that initialization, they kind of like refine the curve such that it meets the condition to be a surface filling curve. And that approach is, well, of course, it is sometimes really robust, but also it always needs a good initialization to give to the system. And so it's not applicable for like, for example, if you have a surface that has a really high genus, then of course that's sometimes not applicable. Or and also like that initialization requires you to do some discrete graph construction based on the discrete mesh, and then that construction is also really expensive in so you need to do all the graph matching stuff based on integer matching kind of algorithms, and that's also really slow. So the benefit of doing this like geometric flow kind of algorithm is that you only need to compute the gradients of that energy, and that's wait, maybe I'm saying something wrong. Okay, sorry, I think I messed up. Yeah.
That's fine. I mean, we can focus on the method that you're using
Yeah.
now as well, but I
Uh,
want to switch figures if we want to talk about that one in a bit more detail. So I
uh,
think
yeah.
figure this one is maybe a
Okay,
better
okay, cool,
just
cool, cool. Yeah.
conceptual illustration of what happens in your method. So you can
Uh-huh.
use this as reference, and then we can start discussing like what more specifically you do in converting
Hmm.
toward the final results.
Okay, good. So basically, given an initial shape, which is curve that's defined onto this surface, like on the very left end of this figure, and like you
Hmm.
have this initial curve, and then you kind of grow this curve such that it fills out the surface, like on the very right end of this figure. And
Right.
basically, how you do that is, so you first assemble an energy function based on the current state of the curve, and then you get the gradient direction of that curve, like on like so. Okay, so you first assemble the energy function that's maybe illustrated in one. Yeah, so energy
Hmm.
assembling using implicit medial axes, and then you, given that energy function, you compute the gradient direction of that energy, which is indicated in blue in here. And then, given those gradient directions, like you kind of, so since if you move all the nodes towards this gradient direction, then there is a possibility that your node is not no longer on the surface anymore. So like you need to kind of project it back onto the surface, and that's what we're doing in the retraction and self-intersection avoidance thing. And oh
Hmm.
yeah, and also you need to you need to avoid these curves to self-intersect with each other. So we kind of do a backtracking line search, which basically first take the step, and then if self-intersection happens, then like you half in the gradient direction, and then like do the back projection again, and like and half it until it doesn't cause any self-intersections. And then finally,
Hmm.
in this dynamic refinement thing, you see the edge lengths, the segment lengths for uh, the whole curve, and then refine the curve such that all the segments have like kind of a uniform length. Yeah. So
Okay.
that's how this geometric flow thing works.
Mhm. I want to get
Yeah.
into the details of this one, the
Hmm.
just energy
Yeah.
assembly in a moment. Before that, though, I just have one follow-up questions on the
Hmm.
self-intersection avoidance.
Yeah.
We'll get to the energy that you go for
Hmm.
minimizing in a minute, but in short, it's composed of two components, right? It's composed of like a repelling force similar to the other
Hmm.
paper, but not the
Yeah.
same. And then there's also a length component to that. Is the
Hmm.
reason why you have potentially self-intersections um, like is the fact that you have a length component in this energy the thing
Hmm.
that causes potential self intersections? Because it seems to me that if
Hmm.
you would just have a repelling force, that you would never actually run into those scenarios. Do you know, for example, if the repelling curves paper that you were referencing before, if
Hmm.
they're simply
Yeah.
using a repellent between them, do they
Yeah.
actually have
Exactly.
to correct for self intersection, or does that only become a problem when you take length into account?
Oh yeah, so I remember that they do some kind of self-intersection detection as well using that approach called CCD. Wait, maybe I need to look up that paper, but like basically they do some
Mm-hmm.
kind of self-intersection detection, and also um, so like these kind of, so I think a common issue about these kind of geometric flows is that even if the energy function is perfect, you still might end up having self-intersections because like, it's just evaluating the discretized version of the gradient of the discretized version of the curve. And like due to some discretization errors, it might get self-intersections. So in that case, you need to kind of do a refinement to fix that.
Mm-hmm.
Yeah.
Okay. Okay. Fine.
Yeah.
Um, Now let's focus on this one. So
Mhm.
I
Yeah.
want to go through the steps of actually
Hmm.
determining this energy, and I think the best thing is to start with the repelling component. I think we have the equation for that here, no?
Hmm.
So maybe we can
Yeah.
start introducing what this term actually refers to. And
Hmm.
I think one point that we'll be referencing throughout this is medial axis.
Oh yeah,
So
right.
maybe
Yeah.
maybe you can just introduce what that is, maybe with the context of this
Hmm.
figure as well, before we jump into the equation.
Okay, so cool. So like, let me first introduce what a medial axis is. So like, basically, if you have a curve, okay, let's think in 2D. So like, first you have a curve that's placed onto a plane, and then given a point, maybe I think I have a figure that's above, I guess. Maybe it's in,
This one?
Oh yeah, over there. Yeah. So
Mhm.
basically you have a curve in 2D, and then you have a point on that curve. And then given that point, you can get the bitangent directions of that point. So like basically if you have this point that's I think it's
Gamma.
like on, oh yeah, so the gamma s. So like
Mhm.
basically
Yeah.
you have gamma s, then you can get the tangent directions. And if you have the tangent directions, then you can get two bitangent directions that are like facing this way and this way. So like if you, I think you can see the orange one, orange sphere
Mhm.
and the blue sphere over here. And then basically, if you grow a sphere that's tangent to this, oh, thank you,
Yeah.
tangent to
Sorry.
this
Let me just
gamma,
zoom in a little bit.
yeah.
There we go.
So if you grow this sphere from gamma s towards this bitangent direction, and then eventually the sphere should hit another point on the curve itself. And so if so, and then like at that point, you can plot the center position of that sphere, and you can call that like m plus s, or if it's the opposite direction, you can call it as m minus s. Then, if you collect all these points, the trajectory of these kind of points that's collected on every single point on this curve, then you can get the curve called the medial axis. And basically, these medial axes are actually used for example, like getting the skeleton structure of like a closed shape, because it's guaranteed to the medial axis is guaranteed to stay on like the center of the shape. So like it's so in computer vision literature, it's like used. So it was kind of intensely used for getting this skeleton structures, but we're in this paper we're actually using it to compute surface filling curves.
Mhm. And your
Yeah.
medial axis is always on the surface of the um,
Oh
well,
yeah. So
on the
it's
surface that you're
mhm.
trying to model, or it's also it can also be internal in the volume that you're
Oh yeah,
modeling.
so that's a really good question. So based on this sphere definition, then like you can, so I think if, okay, so I think I only explained the case of in 2D, but like if it's on the surface, then like you'd like to have a point on a curve, and then like given the two bitangent directions, you might want to grow a sphere, but you can measure the size of the sphere by either in Euclidean distance or geodesic distance. And I think I have a figure below. So yeah, so basically if you have these two spheres, then like you can measure the radius of this sphere in Euclidean distance or in geodesic distance. And if you use the Euclidean distance, then well, of course, the Euclidean distance is very fast to evaluate, but on the other hand, it gets some interference from other parts. So, for example, if you see this like trouser model, and like on this trouser model, there are two surfaces that are kind of facing back to back, and on
Mhm.
those regions, if you grow the sphere towards the bitangent direction, then it eventually hits a curve that's on the backside of this surface instead of the actual medial axis that should stay, kind of in the neighbor area of the surface. And in that case, the medial axis kind of gets messed up, and you can see that if you use the Euclidean distance, you'll end up seeing like a void area in the middle of this trouser. Whereas if you use the geodesic distance, which is basically the measure of how distant you are in the surface domain, then you can see that this medial axis doesn't get messed up by like any other regions on this surface. So you can get a really clean result. But the downside of using the geodesic Euclidean geodesic distance for medial axis computation is that it's really slow.
Okay.
Yeah.
Okay. So with that in mind, then let's switch back to
Mm-hmm.
the discussion on energy levels.
Mm-hmm.
I don't know if there's anything more to say on this one, but I guess we're finished here and can move over to
Mm-hmm.
the equation, right?
Mm-hmm.
Okay. So we have this one, and then I'll let you
Yes.
explain what we're looking at.
Mm-hmm. Oh, I think did you scroll down a bit so that we
So
can
yeah, okay,
see
this one's the
question
full, and
two?
then this, yeah, okay, we can start with the full one if you want.
Right. So basically, we have this energy function. So I think I said that in our geometric flow, we first assemble an energy function and then take the gradient direction of that energy. And so the energy function basically looks like the equation 2 that we see in the screen now. So it's an addition of two terms. So one is the total length of the curve, and the second is the medial axis energy. So basically, the medial axis energy, so like basically the curve length is, of course, really intuitive to think about, right? Because if you have a curve on a surface, then you can measure the length of the curve really easily. And I think like one thing that's not intuitive in this form is the medial axis energy. So basically, the medial axis energy is defined as in equation 1. Basically, this energy function is the square distance to the medial axis for both directions. So one is described as m plus s, which is the medial axis that you get by growing the sphere towards one tangent direction, and m minus s is the other, which you can get by growing the sphere towards the other direction. And you add up these two square distances, and you get the medial axis energy like this.
Okay, and these are Euclidean distances, or what kind of distances are we
Okay, so so of course you can measure it in two ways. So like in one way you can measure it in Euclidean distance, but you can also measure this in geodesic distance as well. Yeah.
Does it matter from the perspective of the algorithm which one you pick, or are they more or less equivalent?
So that's actually the one that I explained in figure 11. So if you choose Euclidean distance, then well, of course the computation is really fast, but you'll end up like the medial axis computation messed up by the nearby regions that are not locally connected. Whereas if you use geodesic distance, you don't get this kind of artifacts, but the downside is that the computation is really slow.
Okay, clear. So that's one part, right? And then we have the length of the curve as well, which is the other part of the energy equation. Would you like to look at something in particular if you want to give a brief explanation of how we derive that result?
Okay, cool. So first of all, I think I need to start from the representation of our curves. So I think you can see that like piecewise linear versus piecewise geodesic figure on the bottom left. Oh, thanks. Thanks for zooming in. So like basically, we actually went through several literatures that does curve optimizations on surfaces, and I feel like most of the cases, people use this piecewise linear representation, which is basically first you have nodes that's placed onto the surface, and then you connect each other with using a straight path that's that's just basically a straight line in Euclidean space. But we found out that instead of using this piecewise linear representation, we found out that using a piecewise geodesic representation is better. So to explain what a piecewise geodesic representation is, so first you have nodes that are placed on the surface, and then you connect each node with the closest path on the surface like this. So this geodesic path is actually, if you see it in 3D, then it should look like a curve, but actually, if you from a viewpoint of a person who's actually standing on the surface, then it's actually a straight line. And so this choice of these two representation actually really matters in evaluating the curve length, because I think could you please scroll down? So I think it's, figure 8, that one. So So we actually found out that using geodesic distances, using this piecewise geodesic representation in our curve allows larger steps in your optimization rather than just using the piecewise Euclidean distance, because you can measure the length of the curve based on the curved surface. So as you can see, our piecewise geodesic representation allows us to go for converge faster compared to piecewise Euclidean distances. Yeah.
How do you see that in this figure?
Oh, okay. Sorry. So maybe I should have explained that first. So basically, so orange is the curve itself, and then the blue arrows, which is the light blue ones are the descent directions, and blue ones are the projected descent directions. on the curved surface. And I think you can see that if you use the Euclidean distance, the paths are pretty short compared to the right one, which we use the geodesic distance in the computation. Yeah.
Okay, so you basically have better alignment between the actual descent direction and the projected one that you ultimately get, so you can take longer steps.
Of course. So
okay.
so I think first you have better alignment, and that's why it can take a larger step compared to the Euclidean one. Yeah.
Okay, that makes sense.
Hmm.
One follow-up question I would have, and maybe I'm getting ahead of myself a little bit, but if we're talking about geodesic distance for a surface that's parameterized according to what we see in the figure here, I'm not sure if you did this for all your surfaces, but assuming you have some kind of parameterized surface that is not mathematically perfect, like it's not a smooth function necessarily, but it's something like triangles like you see here.
Yeah, right. Yeah.
I would have assumed that the final solution that you get is dependent on whichever granularity you have in this representation. But it seemed, upon looking at one of the figures in the results, let me see if I can find it, that you're actually agnostic to that. It's this one, yeah. Okay, so it's early. This one, figure 4, right? So
yeah, right, exactly.
When we're talking about distortions for as a consequence of the granularity, what do we actually mean when we say that? Do we mean like running one assessment, one generation of the curves, and then subsequently altering the granularity, or altering the granularity during the course of evaluation? Like, what do we mean when we say that? Because it seems to me like the distance, at least, that you would calculate is not agnostic to the granularity of your representation.
Yeah, so first of all, if I understand your question correctly, so I think you're asking, so if the underlying surface has different like resolutions, like for example granularity, then like whether my method is agnostic to that or not.
Exactly.
Right? Yeah.
So if it wasn't agnostic, then your energy, as a consequence of changing the resolution, would not remain constant.
Oh yeah, right. So first of all, yeah, I think it's pretty much independent from this figure. So like basically so let me first explain what I actually intended in this figure. So
Sure.
like basically so so what I wanted to tell from this figure is that there was this previous method named variational surface cutting, which was published by Sharp and Crane in 2018. So their curve representation was using a implicit function that's defined on the surface mesh. So like first, if you have the surface mesh, then like you define a function on that surface, which is basically represented by having values at each vertex, and then like interpolates the values on the face by just linear interpolation. So in that case, and also to get the actual curves on that definition, you take the zero level sets, which is basically like, if you have a function on a surface, then like you can take the curve that such that it follows the line that has a zero value of the function. And so that's how they represent this curve on a surface. So, but the problem of that representation is that if you lose the resolution of the surface mesh, then like you'll end up having a really messed up representation of these kind of curves. So, for example, if you have like a vertex number of 10K, and then the mesh resolution is high enough to like even accommodate these kind of like wiggly curves on the surface, but as you decrease the number of vertices, then you'll suddenly end up having these kind of messy arrangements. And so but in our case, as I explained, we adopted this representation called piecewise geodesic representation, which basically allows you to place your node everywhere on the surface. It might be on the face, it might be on the vertex, or it might be on the edge, wherever. And then you also connect these nodes based on the geodesic path. So like in that case, like even if your surface mesh is really coarse, like on the very right sphere on this figure, like you can still get a result based on that representation, because like what you actually need is just the geodesic path, geodesic length between each nodes, and not like for example, the implicit function that's defined on your surface mesh. So that's what I kind of intended in this figure. And also, like regarding your question about like whether it gets affected by granularity of the underlying mesh, I think that's correct. I think it's that the granularity still affects the final result. So of course, like if you have a really fractal, like wriggly surface, and and also if you have like a decimated version of that mesh, then like you'll end up getting two different results from that, because like the geodesic length computation would also get altered by how like fine that surface is or stuff like that.
Mm-hmm. That makes sense. But I guess that's not really our intention isn't really to have a unique curve anyway, right? As far as I understand this, we don't really care exactly how it ends up.
We don't care.
Like that. I mean, another follow-up question on that would be whether this is deterministic or not. Like if you generate two surfaces from the same, or if you generate two curves on the same surface, is this algorithm deterministic or is it random in some way?
Oh, so that's a pretty good point, actually. So I think I think that it's not deterministic at all, because like first of all, if you see this figure 4, then like you can see that even though the overall shape of the underlying surface is kind of similar, it gets a totally different result right here, like on this sphere. So in that case, like our method is not deterministic at all. Yeah.
But if you generate it with exactly the same setup 2 times, does it give you the same result then?
Or... Oh, in that case, it does give same results. Yeah.
Okay, so then it's highly sensitive to changes in the underlying structure, but not necessarily non-deterministic. So non-deterministic, I guess, would be like if you started 2 times on the same one, that you could end up with completely different.
So there are no like stochastic like randomized stuff that's involved in our algorithm. So as long as you have a fixed surface and a fixed initialization, you'll end up getting the exact same curve.
Okay, cool.
Yeah.
So then maybe we can talk about what the big performance increases with this approach are. So I think the main benefit that you list in the paper is that this approach, although it introduces some approximations, is significantly better performing in terms of computational time than the existing counterparts.
Right.
Could you elaborate on why that is exactly?
Okay, so could you please go down to, I think it's figure 5 or something. So there's this, figure 5. So,
maybe this is a bit too much. There we go.
Okay, cool. So, one benefit of our method is that during your decent direction computation, you only need to invert a sparse matrix instead of a dense matrix. So first, I'd like to elaborate what a sparse matrix and dense matrix is. So like if you have a matrix that's n times n, then if in a dense matrix, you'll find lots of elements that are non-zero, whereas in a sparse matrix, you find so most of the entries are 0, except for a really few cases that are non-zero. So, and also it is well known that if you have a sparse matrix, then you can do the linear solve really fast. And so our method leverages from that fact, basically. So like if you have if the energy, it can be defined using So if the gradient direction can be derived using a sparse linear solve, then your decent direction computation will be really fast. So as you can see in the left of this figure, so like basically we compare this with the repulsive curves paper. So like if you see, so the colored elements are the non-zero elements inside this matrix. So if you see the matrix of the repulsive curves paper on the left, then you can see that lots of colored entries inside your matrix. Whereas in our matrix, you can see that all elements are kind of concentrated on the diagonals in the center. And so you can see that our matrix is sparse enough, and it's really fast to get the linear solve. And actually,
What's
if you see, oh, sorry, go ahead.
I was just going to ask, what's the reason for the diagonalization? So clear, like if you
Uh-huh.
have a matrix that's diagonalized or close to diagonalized, it's very fast to invert, and so solving
Yeah,
linear
right,
systems on
exactly.
that is easy. But
Mhm.
what is it with your approach that causes the matrix to be close to diagonal like this?
Okay, so basically our energy is a two-term energy. So one is the total length of the curve, and the other is the medial axis energy. And for the first energy, basically, if you want to compute the length, then all you need to do is first, given a single node, then like you first, for all the segments, then like you can just add up the length of it, and like basically that only depends on the two ends of that segment. So like basically, if you think of a single segment, then like you have two nodes that are uh, like bounded. And then, so if you think of like the first order derivative or even the second order derivative, like if you, per node, then all you need is the incident nodes. And like you don't need to consider like the nodes that are far away from that node or like something else. So like basically, um, if you think of the length energy, what you only need to consider is your neighbors, not like random uh, uh, nodes in your curve. So that's one. And also for the medial axis energy, in our energy computation, we kind of momentarily fix the medial axis point such that like even if the node position changes in our energy function, we don't consider the change of the node positions over there. So in that case, so it's purely just the elastic energy between the 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 medial axis point and your original node point. So basically, in that case, like it's just the energy function can be determined by using just identity matrix. And so in that case, um, the Hessian, the second order the derivative of that of the medial axis energy should be concentrated on the diagonals of the matrix. So in that sense, as I mentioned, so the length energy only considers the neighbors of that node, and also in the medial axis energy, you only consider it yourself. So basically, so all the elements should be uh, concentrated on the diagonals, which is basically yourself and your neighbors. So yeah, that's kind of the reason.
Hmm.
If that
And how
makes
does that?
sense. Yeah.
It makes sense.
Yeah.
How does it compare
Uh-huh.
to the previous paper? So do they consider
Uh-huh.
an energy where all of the different points or all the different
Oh yeah,
nodes
exactly. So
contribute
like in the
to the
previous
energy function?
paper, mhm,
No.
yeah, so good point. So like in the previous paper, they need to, so given a node, they need to evaluate all the possible node pairs inside the curve. And of course they do propose a way to circumvent like computing all the pairs between them, like by introducing some multi-grid resolution hierarchy, or like even using some multiple methods. But still, even if you use like a multi-grid technique, you cannot escape from construction of a dense matrix, and which still hinders this method to be faster. Whereas in our setup, we only consider our neighbors and the node itself. So we don't need to deal with all those dense linear solves.
Hmm.
Yeah.
Which one do you think is more accurate? Like as far as getting accurate results go, it
Mm-hmm.
seems to me just off the top of my head that taking all the points into account is more accurate and that you're making an approximation that makes it faster. My
Mm-hmm.
follow-up question would be, and I know there were a couple of scenarios where
Mm-hmm.
your solution breaks down, like few and far in between, but nevertheless a few where it breaks down. Do you think
Mm-hmm.
the assumption here on the medial axis being the only thing that contributes to the energy besides the length of the curve then, do
Uh-huh.
you think that's the source of it? Because arguably you're not taking into account like the full interaction between points, because if you're
Yeah,
looking to
right, right,
establish some
right.
kind of energy, you're all the points would have an effect, even though
Mm-hmm.
like it's well, potentially it attenuates with r squared,
Mm-hmm.
right, if you
Yeah,
move
right,
away
right,
from it,
right.
so
Yeah.
the
Mm-hmm.
contribution will be small but nevertheless existent.
Mm-hmm. Oh yeah, so that's actually a really good point. So I feel like one effect that's coming from the fact that we're only considering the energy locally is that if you see the results of the previous method in ours, you can see that ours is pretty much more wiggly compared to the previous one. And I feel like that comes from that fact. Like since we're only considering the energy locally, there's a high chance ending up having a curve that's like kind of like really that is satisfying the surface filling constraint only locally, but like doesn't satisfy it. Well, maybe like, so for example, if you consider the global energy, then like it should converge into a single configuration where the energy is totally minimized. But like, since we only consider locally, it can, and there are like multiple situations where your gradient will be zero, but like still there are no single like optimal points in your energy optimization. So yeah, I think that's pretty much the difference.
Okay, cool.
Yeah.
So we talked about one approximation in the form of the energy function itself, and then we have a couple of approximations when it comes to linearizing the system for solving. Would you mind elaborating on like what exactly we do? Like what approximations is it that we put in place? For example, here would be one starting point on the length curve in this case to actually get an expression that we can evaluate.
Okay, so so in our energy minimize, so I think we use two approximations. So one is in our medial axis energy, and another is in our length term. So I think you're showing the length term right now, so I'll explain it first. So like, if you scroll down a bit, I think there's a figure that's explaining how to flatten out the geodesic path, or maybe it was above. Sorry. Oh yeah. So since we adopted this piecewise geodesic representation, it's impossible to evaluate the like first or even the second order derivative based on the geodesic length by just like considering the Euclidean distance. So to do this, instead of like considering the length on the curves domain, we first apply rigid transformation and map these 2 points that are that bound this segment onto a single plane, such that the rigid transformation of one point gets to the origin of that plane, and the other gets onto a point that's on the x-axis like this, like on the bottom right over here, bottom right figure over here. And on this plane, of course, you can like get the the quadratic length of this geodesic segment on the plane, and then like you can like get the first order and second order derivatives on this plane. So that's one approximation that we use. And also the second one is the medial axis computation. So yeah, could you please scroll down a bit? So to the medial axis, I think it was like 3 point.
Here,
oh yeah,
right?
that one.
Yeah.
Oh yeah. So okay, so I think it. So I think. Oh, could you scroll a bit? Oh, scroll. Could you zoom out a bit so that we can see this figure and like equation? That equation.
You want the first one?
Thank you very much.
Okay.
Oh yeah. So like basically, what we do is we compute the medial axis positions per node, and then like given those two medial axis positions for like one direction and the other, we add the quadratic version of the length between the node and the medial axis, and then add it for the two medial axes. And then for this, we use so during our energy assembly, like we momentarily fix the medial axis points and like just treat it as a constant point. So like no matter how the node positions change, we make an assumption that this medial axis position still doesn't move. And in that case, all we need to do is first like get the medial axis position and then feed it into this energy function over here. So yeah, that's the second approximation over here.
Okay. Yeah. So it seems to me, and correct me if I'm wrong here, like both of the approximations that you're making actually resolve themselves. So stop being approximative as your step size goes to 0. So they're not like, you can effectively, by putting in more computational power, remove that part of the assumption.
Oh yeah.
Or at least limit. I mean, at least limit the role which it has in your convergence.
Yeah, good point. Let me figure out. Yeah. Yeah, so I feel like the first one, like regarding the first one to consider the length minimization, then I feel like as long as, so if you have like a really fine curve that has like a really short edge length, then of course I think it'll like the error would be like really small. But like in the case for two, like we kind of give an assumption that the medial axis position is constant, even though the node positions are actually moving. So in that case, I don't think like making the curve resolution finer would mitigate the approximation error over here. Yeah.
Agreed. But what
Mm-hmm.
I mean is not making the curve resolution finer, but rather making the step size in your gradient descent more fine-grained.
Oh, yeah. Uh, oh, yeah, right.
So you would need to tune
Uh,
both of them, I guess. Like it's not enough to
yeah.
improve the granularity in one dimension, but you would need to improve it like both in terms of representation of the surface and in terms of representation for the stepwise gradient descent.
Mhm. Yeah, right. Yeah, so actually I think we need to go to so like there's a figure, I think it was like on the very end of this paper, maybe figure 26 or 7 or something like that. Yeah, so like even if you so I think I said that we in our gradient computation we momentarily fix the medial axis points. But like imagine if we like move the medial axis points, so like if we make the medial axis position dependent to the node positions, then what actually happens is that you'll end up getting a really messed up result like here. So 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 maybe you could see that the green plot and also the light blue plot is the one that we use when is the result of our energy minimization if we move these medial axis points. And like actually, we couldn't figure out why this doesn't work. And like, so and like we don't have like a kind of a definite thought about this. But like I feel like still the gradient direction kind of gets messed up because of the discretization error or something like that. And then this optimization will eventually stop because like even giving in this situation, even if you give even a small step, even a smallest step in your gradient would still like give you self intersections, and like the curve generation wouldn't like go further than this. Yeah.
Mm-hmm. Okay,
Yeah.
understood.
Mm-hmm.
Good. I see that we should start wrapping up. I just want to give you
Oh
the
yeah.
opportunity before to give like a quick elevator pitch for the main results that you have and any other things that you think are worth like really highlighting of your paper before we close.
Mm-hmm. Okay, so we propose a we propose a geometric flow algorithm to compute surface filling curves in a really fast and robust manner. And like we achieve this fast result because we use we leverage a linear solve of sparse matrices instead of dense matrices. And also, our method is robust because we use the piecewise geodesic representation instead of representing the curves with an implicit function. And this method works even on a coarsest mesh of the surface. And so this improved speed and also robustness would, I hope, that would lead to a broader application scenario such as like robotic path planning, or like, oh, maybe that one like figure 27. So I was pretty excited to make this rendered figure over here. So like maybe it could be applied for heating or cooling applications. So yeah, so I hope you'd enjoy it.
Mm-hmm. Very good. Your contact information will be in the description and the links I provide. Thank you very much for taking the time to go through the paper. I enjoyed it. And
Thank you very
that's
much.
it.
Yeah.